Welcome to our new lecture on hyperspectral image analysis. In this lecture, we will mainly discuss about unmixing and hyperspectral image enhancement. In the previous lecture, we have already started discussing about unmixing. We have discussed briefly why unmixing is desired in the case of hyperspectral image analysis. Often, linear mixing model is employed traditionally in the case of the hyperspectral image analysis. The spectrum of each pixel in the case of linear mixture model is approximated by a linear mixture of end-member spectra weighted by the corresponding fractional abundances. However, this traditional linear mixing, they also show several constraints, such as they use the non-negativity of the abundance, and that should sum to 1, and these constraints improve interpretability in the case of linear mixing. Now let us start thinking about deep learning based unmixing. One possibility is to use 1D convolution with spectral vector of a single pixel as input. The workflow will look like this. The CNN would extract hierarchical spectral features. The output neurons, in this case, correspond to different end members. Outputs are normalized to obtain the abundance fractions. Thus, in this case, the training strategy will look like this. Each training pixel is assigned a binary target vector. The neuron corresponding to the true material is set to 1. All the other neurons are set to 0. So in this case, what we are seeing is that the training itself is not even taking into account the abundance here, whereas the output that we get from the network, the final layer, it can use a sigmoid activation or even could use softmax depending on exact implementation of the architecture. However, this is now giving you a value between the 0 and 1, and this is giving us the notion of abundance. So what we see remarkably here is that the training itself was not with that abundance, rather we had a binary vector. However, still when trained in this way, we expect that the output, this will produce the abundance for us, and this can also be extended to 3D convolution. Here, one aspect we need to consider is that the pure material spectra may not be known always. We can assume, of course, like, okay, for simplicity, that this is known, but it's not always that is the case. In that case, we have to deal with this additional problem of end member extraction. End member extraction identifies the representative spectra. So this then becomes a pre-processing step, or rather like how you actually model the problem. Sometimes like, okay, you are finding the end member spectra and abundance simultaneously. Often, not all the methods, many methods actually assume that the pure pixels exist in the given image. This is called pixel purity assumption. Thus, this assumption and the methods which make this assumption, of course, they may fail in the highly mixed scenes where there are no pixels which correspond to the pure end members. Now, talking about specific DL-based techniques or architectures for unmixing, one natural candidate is the autoencoder. Autoencoder formulates unmixing as a spectrum reconstruction problem. The network receives a hyperspectral pixel spectrum as input. The encoder compresses the spectrum into a low-dimensional representation. This representation then, of course, has to be decoded by a decoder. However, this representation, low-dimensional compact representation, this is interpreted as the abundance vector. And to interpret this as abundance vector, of course, we need to enforce some additional conditions on them, such as non-negativity and etc. What one would do on the top of this is that use a simple linear decoder to reconstruct the original spectrum. Thus, we need to implement training process in such a way that it encourages the latent representation to correspond to the abundance, whereas the decoder waits to correspond to the end members. So these are the two unknowns that we mentioned, right? The abundance and the end members. The latent representation, this is giving us the abundance, and the decoder weights, this is helping us to provide the end members. However, we have to understand that, okay, we are working with a simple linear decoder to reconstruct the original spectrum. So think of like this: we have 200 spectral bands, and let's say we have 5 end members. With encoder, we will be projecting to then R5. Now, so the 5-dimensional vector, right, will be projecting with the encoder, and then with the decoder, we are going back to the original 200-dimensional vector. So here, as we see it, that our decoder is linear. This means this is essentially a 200 cross 5 matrix, where each column of the decoder weight matrix is an end member spectrum. Again, to understand the architecture, the bottleneck layer, this contains one neuron per end member. Encoder learns how much of each material is present in a pixel. Decoder combines these materials to reconstruct the spectrum. Decoder weights thus gradually become in the training process, gradually it becomes the end member spectra. Now, let us move ahead to our next topic, that is the hyperspectral image enhancement. However, before going into the nitty-gritty of image enhancement, let us very quickly recap through generative adversarial network. We have studied about generative adversarial network before. We said that given, let's say, Z, a latent vector, we have this generator which is producing GZ, which we expect to be in the training process at some time to become indistinguishable from our real world sample X. And in addition to the generator, the architecture also consists of discriminator, which is taking either X as input or GZ as input. And it's trying to distinguish. The task of the discriminator is to distinguish the fake samples, that is GZ in this case, and the real samples, that is X in this case. And the generator is trying to, in the training process, generator is trying to fool the discriminator. We also briefly mentioned already when we discussed the GAN that it can be like many other downstream applications. It can be used for, let's say, the synthesis of hyperspectral data, where how it would look like given the latent vector, the generator is producing the synthetic spectra and there is the real spectra. Discriminator takes the real spectra, synthetic spectra, it tries to distinguish between the two. We also talked about the conditional GAN, where we are adding additional condition input to the generator. Often, this additional condition is class information, thus we'll call it class condition GAN in that case. However, of course, like there are different versions of the conditional GAN where it can be like some other input, like an image as condition. We are trying to produce another image, which brings us to peaks, let's say, where we had this image X as input, and given this G, we are producing this generated image GX. And this now again, like the discriminator tries to differentiate between the fake and the real samples. And then of course we also talked about like even more advanced versions like cycle GAN, let's say. Now with this background, let us quickly jump to our discussion on the hyperspectral image enhancement. Enhancement improves quality and usability of the hyperspectral images. Enhancement is a more of a bucket term. It may include denoising, it may include super resolution, may include inpainting. There can be also other kind of enhancement that one could possibly think about. However, these are the three things we will focus into this lecture. Enhancement is important, quite important in the real world remote sensing systems. Hyperspectral sensors often suffer from noise for different reasons. May also be impacted by cloud and other artifacts. Spatial resolution of hyperspectral images is often quite limited. This is one reason we would probably like to apply some kind of super resolution. And then we can have, missing pixels, corrupted pixels. So cloud could be one particular reason of this missing or corrupted pixels, right? However, there can be other reasons as well. On the other hand, the challenges in the hyperspectral image enhancement include the hundreds of spectral bands that increase complexity, spatial and spectral correlations must be preserved while doing the hyperspectral image enhancement, and noise characteristics in the hyperspectral image may vary across bands. Often, the image denoising assumes Gaussian noise, which is modeled as random additive perturbation. This affects all spectral bands. So often in our research type synthetic settings, we assume Gaussian noise. However, what we also see is that the hyperspectral image is often impacted by more complex noise, such as stripe noise is one such example, which appears as vertical or horizontal stripes. Thus, it's more challenging to model or solve. The hyperspectral denoising removes unwanted signal perturbations, while the goal is to also preserve spectral fidelity. Spatial filtering could be one option there, which process spatial neighborhoods. Mean filter, Gaussian filters, they can be used. They are indeed quite simple, but at the same time may blur details, and they also have limited spectral modeling capability. Spectral filtering is often combined with the spatial methods, so they are meant to preserve spectral continuity. Now, with this background, let us think about deep learning for denoising. One straightforward approach is to use self-supervised learning in this context. Let's say we are given noise-free image. What we can do is that we can easily corrupt those images by adding noise. And then the task would become to reconstruct a noise-free image. Expectation is that in solving this particular pretext task, the model learns denoising. So, of course, in this context, one would recall denoising autoencoder, where we have the encoder-decoder architecture, and let's say the noise is added, and the output we are trying to get back the denoised version of the input, in this particular case, hyperspectral image. One can also use generative adversarial network for denoising. Given the noisy hyperspectral patches, what one can do is that one can, with the generator, get the reconstructed hyperspectral patch, and this we can here use reconstruction laws as well as with a discriminator which is fed with the reconstructed hyperspectral patch as well as original hyperspectral patches, a discriminator trained with the adversarial laws. Here, one important aspect that we need to keep in mind is that not all the bands are similarly noisy. There are bands which are more impacted by noise, there are bands which are less impacted by noise. Of course, sometimes it's the case that as a pre-processing, some of the bands are even dropped. But even if not dropped, what is often done is that many methods during the denoising distinguish between these low noise and the high noise bands. Following this, the low noise and the high noise bands are treated separately. Now we'll discuss about the next enhancement topic, that is super resolution. Super resolution enhances spatial resolution. Indeed, in the case of the hyperspectral images, even though with such a large number of spectral bands, we have very rich spectral information, often this is the case that the hyperspectral images have limited spatial resolution, and this motivates us to generate high spatial resolution hyperspectral images, which becomes useful for fine-grained analysis. So the first possibility we'd like to consider is single input super resolution. So in the case of the single input super resolution, we'll use only low resolution hyperspectral input. And with this, we need to somehow learn mapping to high resolution output. This kind of paradigm widely adopts deep learning, how we are downsampling the high resolution hyperspectral images are artificially degraded using some known downsampling operation. The degraded image now acts during the training process as the low resolution input, whereas the original image, this will act as the target. So we have to understand here there are three different resolutions that we are working with. In the very first point that I am talking about, high resolution, so think it to be lying somewhere in the middle. Okay, so this is the high resolution. I mean, this is the one which we are given with. However, we want something even better, that is higher resolution. Okay, while doing so this high, higher, and then there is something called low. So from this high we go to low. Now during the training process, what happens is that this low acts as an input to get back high, and when this model training has been done, the assumption is that now during the inference, even if the high resolution now is given as input, the model should be able to give us back the higher resolution. Okay, so from low to we go to high during the training process, from high to we can go to higher. This is the assumption with which this works, and this approach is often, of course, also used beyond hyperspectral images also. Again, generative adversarial network can be used for hyperspectral image super resolution, where a generator produces high resolution hyperspectral images from low resolution inputs. A discriminator distinguishes the generated images from real high resolution images. Adversarial training encourages more realistic spatial details. Additionally, we can incorporate reconstruction type laws to ensure spectral signatures remain accurate or aligned. One can also think about representative band super resolution. So instead of going for super resolution on all bands at the same time, what one can do is super resolution can be performed on selected spectral bands of interest. Representative bands can be chosen through band selection mechanism, which we have discussed before. Then the high resolution information learned from these representative bands can be used to further guide the reconstruction of the remaining bands. Of course, depending on some particular application, one could just upsample these particular bands and not even bother about the other bands. That's also quite possible. And this approach reduces computational cost while maintaining most of the spectral information. Now, the super resolution, we say that super resolution with just single input of hyperspectral image. However, in practice, what is done is that super resolution is also done in a more pan sharpening kind of approach, where in addition to the hyperspectral image, an additional input is given, such as a RGB image or even like a single band image, or some multispectral like more than 3 band image also, which is higher resolution. We have, let's say, this 200 band image, hyperspectral image, which is lower resolution, whereas some 3-channel RGB or like 4-channel multispectral or some 1-channel image, which is of much higher spatial resolution. Now this, let us think, like for simplicity, let us think that this we are talking about is indeed RGB images. This provides us with higher spatial details, whereas the hyperspectral image provides spectral richness, and these two, we go for a kind of fusion which helps us to improve the reconstruction quality. There are several ways that one can do this. Of course, one can do this using deep learning kind of approach as well. Now, the last topic that we'll discuss in hyperspectral image enhancement is inpainting. Inpainting restores missing or corrupted regions important for damaged hyperspectral images. It preserves. The goal is to preserve the spatial and the spectral consistency while restoring these missed regions. So this is a very simple illustration. Given a particular image, we have like a particular area in this which is missing. One could traditionally use some kind of interpolation based inpainting, where missing pixels are estimated from the neighbors. However, this kind of approach is limited for like when this gap, the black region that we saw in the last slide, this keeps on growing in the size, and this kind of approach becomes quite limited. Inpainting, when you start thinking about more from the deep learning possibilities, inpainting can be modeled as self-supervised learning. Random pixels, patches or regions are intentionally marked during the training. The model receives the partially observed image as input, and the reconstruction of the marked regions thus becomes the learning objective. And thus in this process, we do not require any external label, making it a self-supervised learning problem. Again, GAN can be used for hyperspectral image inpainting. In this case, a generator would predict the missing regions from the surrounding spatial and spectral information. A discriminator evaluates whether the reconstructed regions appear realistic. Thus, we are towards the very end of our discussion on the hyperspectral image analysis. However, before ending this, let us remember the sensor shift problem that we have mentioned before, that models trained for one hyperspectral sensor may not work effectively on another hyperspectral sensor. So this is a significant barrier to applying, like even if you have trained for a particular sensor, how do you really transfer to another sensor? So here I will leave you with this homework, which sometime hopefully when we later discuss change detection, we'll come back to this discussion. But for now, I'm leaving it to you to think about, like, can you think about some approach to at least get benefits out of the deep networks when, like moving around these sensors, like you were given with a novel sense sensor, hyperspectral sensor with a totally different band combination. So what one could do to the exploit the property that the deep networks often give us, like rich feature, without going into like training, audit training. Okay, with this I will end our discussion here. Thank you.